In this video, we're going to learn how to find power produced by a car engine. Let's start by looking at an engine and how it works. This, of course, is a car engine. The parts that are creating the work are inside. Inside the engine, we have cylinders with pistons attached to a crankshaft. With each rotation of the shaft, pistons in the cylinders move up and down. Each time a piston goes up or down, it is a stroke. There are 2 strokes per rotation. Most engines are 4-stroke engines, meaning that the whole combustion process takes 2 rotations to complete. Each stroke in the combustion cycle has its own stage associated with it. The first stroke is the intake stroke. In the intake stroke, the intake valve is open and air is drawn into the cylinder as the piston moves down. The next stroke is the compression stroke. Here, the intake valve is closed and the piston, which is now moving up, compresses the air in the cylinder. In the third stroke, gas is added to the compressed air and a spark ignites the gas-air mixture. As the combustion occurs, the air expands, helping the piston go down. The last stroke is the exhaust stroke. Here, the exhaust valve opens and the piston moves back up, pushing out the exhaust. An easy way to remember the stages is suck, squeeze, bang, blow. Because intake sucks, compression squeezes, ignition is a bang, and exhaust blows the gas-air mixture out. So how does this process determine how much power a car engine can produce? Power is what we usually use to measure how strong our engine is. In reality, power is work over a period of time. As we had seen during the ignition stage, the expansion of air caused by the combustion process produces work and helps the piston move down. This is the work that your engine is producing. We can find this work using thermodynamics. Let's start with the definition of work. Work is the product of a force on an object over a distance, W equals F ds. We can look at work as an integral of F ds. In thermodynamics, F is pressure and the distance is the volume. So work is an integral P dV. Since work is an integral, it will be easy to understand how much work each process is producing by looking at a PV diagram, since work is an area under the curve. So a good place to start to understand the combustion engine is to look at its PV diagram. This is the actual PV of the combustion engine. As we see, it is very complicated and would be very difficult to analyze. To make analysis easier, we used an idealized cycle called an Otto cycle. The Otto cycle still undergoes the same processes, but these processes are simplified in such a way that we can use basic thermodynamic models to describe each process. Basic assumptions that the Otto cycle makes to make analysis easier are that heat is transferred across the system boundary instantaneously, and that air is the working fluid and can be modeled as an ideal gas. The ratio of gas to air is so low that we do not need to consider the mass of the gas to the system in the combustion stage. Each process in the Otto cycle also has its own assumptions. The first process goes from stages 1 to 2 and is an isentropic compression, meaning that entropy is constant, so no heat is crossing the system boundary. The second process from stages 2 to 3 is a constant volume heat transferred to the air. The third process is an isentropic expansion, again meaning that no heat is crossing the system boundary. And the last process is a constant volume heat transfer from the air. As we see, each of these processes still corresponds to the stages of combustion. Now we have to figure out how to use these assumptions to find the work produced. Let's start with the first law of thermodynamics. It is the first law, so it is where we should begin. The first law of thermodynamics deals with the conservation of energy. It states that the energy that crosses the boundary is equal to the change in energy in the system. Here, delta U is the change in internal energy. Q is the net energy across the system boundary by heat, and W is the net energy across the system boundary by work. Since air is an ideal gas, the change in internal energy is also equal to mCv delta T, where m is the mass of the working fluid, Cv is the specific heat at constant volume, and delta T is the change in temperature, T2 minus T1. Let's now add what we know about the first law of thermodynamics to what we know about the Otto cycle. We know that the first process from 1 to 2 is isentropic, and that there is no heat crossing the boundary. Therefore, Q equals 0, and we are left with the work that crosses the system boundary, W12, equal to mCv T1 minus T2. The second process from 2 to 3 occurs at a constant volume. In order for there to be work, there has to be a change in volume. So no change in volume is no work, and W is 0 for this process. And therefore, Q23 is mCv T3 minus T2. The process from 3 to 4 is another isentropic process. It's the isentropic expansion. So once again, Q is 0, and W is mCv T3 minus T4. The last process is a constant volume heat transfer, so work is 0, and Q41 is mCv T1 minus T4. Using our first law analysis of the Otto cycle, we can find net work. W in, which is W12, which we know what that equals, and W out is W34, which we also know what it equals. W net, if it's of course equal to W in plus W out, which comes out to be mCv T1 minus T2 plus T3 minus T4. Now that we know how to find work, let's do an example to find the power produced by an actual car. The car that I'm going to find the power for is my first car, a 1996 Cadillac DeVille. Online, you can find all the specs necessary for finding what is needed to find the power of an engine. We need to have the engine configuration, the cylinder bore, the cylinder stroke, the power so we can compare our results, and an RPM, which we will use in our calculations. We also need compression ratio and max temperature. The volumes we need are swept volume and clearance volume to find the min and max volumes in the cylinders. The swept volume is the volume swept by the piston, which is pi times the stroke times the square of the bore, all divided by 4. The clearance volume is the volume minimum. To find this value, we use the compression ratio and swept volume. This is because the compression ratio is the ratio of the max volume to min volume, and the max volume is the clearance volume plus the swept volume. We also start with some known values. The initial pressure, P1, is the same as atmospheric pressure, which is 101.325 kilopascals. The initial temperature is also the atmospheric temperature, which is about 300 Kelvin. The max temperature that an engine can withstand, or specifically this engine can withstand, is 2,310 Kelvin, which will be used for our T3, temperature at stage 3. Cv and K, which are the specific heat constant with constant volume, and the ratio of specific heats, can be found on tables of properties of air. Since we know that net work is mCv times T1 minus T2 plus T3 minus T4, we need to find m, T2, and T4. Since air is an ideal gas, to find m, we can use one of the relationships of an ideal gas. This relationship is that PV equals mRT. So m equals PV over RT. We have all of these values, so we find that the mass is 0.000737 kilograms. To find the temperature at stage 2, we first have to find the pressure at that stage. Since the process from 1 to 2 is an isentropic process, there's a nice relationship between the pressure and volumes at both stages that we can use. This relationship is P1 V1 to the K equals P2 V2 to the K, where once again, K is the specific heat ratio. Using this relationship, we can find the value for P2. We can then use the relationship of ideal gas PV mRT to solve for T2, since now we have all the values we need. T2 ends up being 762.53 Kelvin. We already have T3 since it is the maximum temperature in the cycle. We do, however, have to find the pressure at stage 3 to find the temperature at stage 4. Once again, we use the ideal gas relationship to find P3. Since the process of 3 to 4 is isentropic, just like the process 1 to 2, we can use the relationship that we used in that previous process, where P3 V3 to the K equals P4 V4 to the K. We then use the known values of P4 to find T4, once again using PV equals mRT. We find that T4 is 908.796 Kelvin. Now that we know the mass of the air in the cylinder and the temperatures at all the stages, we can find the net work produced by a cylinder. This comes out to be 0.50125 kilojoules. We have the work, so now it's time to find out how much power your engine produces. Since the work we found was only for one cylinder, we have to multiply it by 8 to get the net work produced by an engine. We also want to know how many times per second work is being produced, since as we learned, power is work over change in time. To find how many times per second work is being produced, we can use the revolutions per minute, RPM, provided in the specs. RPM is how many times the crankshaft rotates in a minute. Since we want our time in seconds, we divide our RPM by 60 to get RPS. Since there are 2 strokes per rotation, we multiply the RPS by 2 to get the number of strokes per minute. We then divide this number by 4, since there are 4 strokes in a cycle, and the work value we have is the work produced by one cycle. We find that the power produced by our engine is 192.5 kilowatts. The power that the spec sheet says is 205 kilowatts. Our 192 kilowatts is pretty close. The value we found is in fact 93.73% of the actual power. We see that using the Otto cycle and idealized cases, we can get a fairly accurate answer for finding the work and power produced by an engine. The end.